Okay. A basis is a linearly independent spanning set. Now, we haven't included all the conditions. Linear spanning set of what? Well, it's a set of vectors. And you would write the set with braces and list the vectors within the set. It's got to be linearly independent. And linear independence means only the trivial linear combination is 0. Remember, a linear combination is a sum of multiples of the vectors by the scalars. The linear combination then cannot be 0 unless you have the trivial case where all the constants are 0, and clearly that's going to give you 0 in any case. So this means that our C1V1 plus C2V2 all the way up to C sub n Vn is equal to the 0 vector. Here's our linear combination to sum of multiples. And actually, I guess I should probably have the arrow going over here to the linear combination. This is 0 if and only if all the C's are 0. If that condition is satisfied, then our set is linearly independent. And this will be, I've got linearly independent so that the set of the matrix you get from the column vectors doesn't end up with a row of zeros, okay? And that's going to be the case, okay? If the V1 through Vn are members of Rn, then you list the vectors as columns in a matrix. If the matrix doesn't end up, if when you reduce the matrix you can't end up with a row of zeros, that means all the vectors are linearly independent. Okay, so that's one test for linear independence, and that's one of the things you have to prove that you have a basis. Okay? Also, it's got to span the space, so that if you take this set of vectors and multiply it by a vector in the space, a column vector in the space, if you take this matrix, again, columns are your vectors, and multiply it by all the different x vectors in the space, and I'm saying it wrong again. Take this matrix of column vectors, set it equal to any vector in the space, and you have a solution for x. That is, there's some x that gives you that vector for any vector in the space. And that means that the set spans the space. It means you can get any vector in the space by multiplying this matrix of column vectors by some vector. Okay? There's always a solution. It always has a solution for any vector b in that space. X also needs to be in that space. Okay, well, that's kind of the feeling of it. Let's apply it. Yeah, I'll come back to this little statement here.